Hello and welcome to this review lecture for lecture 7 to 9 and basically this were all about electrochemistry and the way that measurements happen electrochemical system. So, we talked about the various calibration methods which were available for electrodes. For example, there were three methods that were specified. One was the direct measurement method, another was the standard addition method, third was the grand plot. And as the theory would go, the direct measurement typically indicated that you have to calibrate an electrode, electrochemical electrode with reference to standard pH solutions. So, you have three different pHs over which measurements are made of the EMF of the electrode, and then you have a calibration plot, and the idea is that whatever readout comes in terms of particular concentration, it would be read directly. The concentration would be read directly by looking at this calibration plot, assuming that the Nernst equation is obeyed and the potential versus log of concentration follows a linear characteristics. So, as we also indicated, this was a method which was more based on experiments and insufficient experiments, because the calibration would really depend on the number of points that you would make. And when the manufacturer decides to make an electrode and sell it, typically not more than 3 or 4 solutions of different pHs are provided because of logistic reasons, and therefore, based on these 3 or 4 points of pH, EMF versus log of concentration relationship may not be accurate representation of the actual calibrated electrode. So, there were requirements felt for different other methods for the calibration. One of them was the standard addition method, where there would be a solution of known concentration of a known volume added to the analyte of interest which had an unknown concentration and a known volume, and there was a series of calculations through which it was shown how the two EMFs with the unknown concentration as well as the concentration after addition of this standard solution were taken, and based on that EMF difference you could correlate what is the unknown concentration of the species in question. So, this was one step further to the direct addition method, because now there would be the possibility of introduction of some variability by introducing a new concentration and let the electrode behave towards the new concentration. So, the randomization which would happen in the measurements as a natural process would be more limited because of this addition and inclusion of that in the calibration scheme itself. The other requirement was that can we do multiple additions, because standard addition was only one step towards this minimization of the random elements for measurements of the potential, and so we did multiple additions, meaning thereby that now you have different concentrated different known concentrated solutions which you would add to your unknown concentration, and then you would plot the 10 to the power of delta E by S with respect to the concentration at hand, and then you would extrapolate it all the way to the point when this 10 to the power of delta E by S would be 0, so that your unknown concentration is your standard concentration which is added. Okay. So, this actually gives rise to a more variability or a more variable nature solution, and EMF being measured every time by the electrode, and then calibration is based on such variability, meaning thereby this would be a more accurate representation of the actual calibration that the electrode should have in measurements. So, after doing these three addition methods, we started talking about ion selective electrodes, and we started briefly describing about how this ion selective nature of the electrode can be introduced. Of ion activity was raised, where ion activity, as defined earlier, is a factor to the concentration of the analyte of interest, which is added because of the fact that there is a substantial interference from the other ions which are present near the target ion in the solution. Okay, meaning thereby, supposing there is a solution which contains the target ions and many other ions which are probably non-interfering in nature, but still they are present, and then the electrode needs to get influenced by electrode doesn't electrode should be in a situation where it need not have any influence from those interfering ions or even non interfering ions, and it should be able to measure the particular ion of interest or the target ion. Okay. So, here the idea is that how the target ion would be resulting in the reduction oxidation process, or how the charge transduction would happen between the electrode and the solution, is also quite dependent on this environment of the target ion. So, as we properly sort of studied that what are the different causes for influencing this ion movement or this charge exchange with the electrode at the interface of the electrode, one of them would be simply that the ions would move randomly with respect to each other in a solution itself because of Brownian motion. Okay, you cannot attain absolute 0, and therefore, at room temperatures definitely there is going to be some motion, some movement of the ions in the solutions. So, then there would be Coulombic forces of attraction between the ions of opposite kinds, and similarly there would be forces of repulsion between ions of opposite of similar kinds, and there is always a tendency that the central ion of interest drags an ionic environment around it of the opposite charge, the opposite nature, although the overall charge neutrality concept would be, or principle would be maintained, but still there are going to be several positive charge centers surrounded by a bunch of different negative charges. Okay. And so, therefore, it is very definite to say that the influence from these Coulombic forces would be substantial in terms of ions moving, getting reduced or oxidized at a electrode solution surface interface, and electrochemistry has to consider these aspects. And then, of course, the fact that whenever there is a localized movement from one such environment to another environment going towards the electrode of its opposite charge kind, where ultimately the charge would be dissuaded or disappear. Okay, there is always going to be some kind of forces or interplay between such environments. So, because of all these complex reasons, it is always important to say that the solution will not be represented in terms of its true concentration. Okay, there is going to be some difference between the true concentration of the analyte and the actual concentration which is contributing towards any EMF change of an electrode. One of the reasons why activity coefficient is brought in, which is typically a factor of the concentration, and it was very clearly illustrated that earlier, before electrochemical theory was not so advanced, probably 1920s or before that, there was always an experimental validation of what is the activity, looking at only the Nernst equation and trying to find out what the log of so called apparent concentration, which is actually the activity, would behave like with the measured potential of an electrode. But later on, of course, there was a theory which was described by Debye and Huckel, and this was detailed in the lecture, where we talked about several aspects of the electrical charges and Coulombic forces between a central charge, which may be positive in nature, to its ionic environment which it would drag. And in that light, we tried to solve the Poisson's equation, which is of course the solution for the potential function, if we consider the central ion to be of spherical symmetry, and if we consider that the potential only varies radially outwards from the center of the ion all the way to the infinite domain or infinite distance from the ion. So, we formed a very good theoretical background about how the ion of interest could actually result in its environment by doing some work by the system. A distribution was assumed at infinity in terms of numbers per unit volume, and then by using the Boltzmann equation, it was sort of analyzed that at the point of interest where the potential function is being evaluated, what would be the charge distribution, because the distribution because of the presence of this distribution at infinity and the potential associated with the central charge. So, we got a series of equations where, by solving for the potential function, finally we obtained a very interesting form of the equation, which was related to a e to the power of minus kr by r, where a would be a constant coming out from the general solution for the ODE in question, and e to the power of minus kr, where r is the radius associated from the center of the ion of interest all the way to the infinity. And this k coefficient was determined in terms of the summary charges of both positive and negative kinds, which was there in the particular environment of a single charge in consideration. So, finally, we tried to find out this A factor by using an equation where we integrated the volume charge density all the way from the surface of the ion, which would be also known as the ion size parameter, all the way to the infinite distance, where the charge density assumes complete equivalence and there is no skewed distribution as happens before infinity of one charge over the other kind. And then we would equate that to the exact magnitude of the central charge, assuming that the electroneutrality principle is obeyed, and from that we could actually find out what the A value is, and subsequently could determine the density of charges near the central ion of interest which was in question. So once we did that, then of course we found out that if we evaluate the potential function at the surface of the charge, which is also nothing but the ion size parameter, it has two contributing components. One component would be resulting from the potential imposed by the central charge, and the other component would be the potential imposed due to the atmosphere, the ion atmosphere, as bound by the central charge. So an equivalent radius for the ion atmosphere was arrived at, and it was actually nothing but 1 divided by 1 by k plus A, where A is the ion size parameter. And subsequently we tried to see what is the work done per mole of the charge in order to bring at least 1 mole of the environment very near to the central charge of interest by virtue of the work done by the central charge itself. Okay. And then equated that to the free energy of the system, which would give us a very important relationship between the activity coefficient gamma I, okay, and the amount of work done by the potential function xi I at a certain point, probably at the surface of the charge at radius r equal to the ion size parameter, in order to contribute, in order to build up an environment around it. Okay. So it is basically the total amount of work done by the system by one particular charge to build an environment of exactly the opposite charge around it. And so with this equating entity, we could actually bring out a very simple relationship between gamma I, the activity coefficient, and several other interesting parameters like the amount of valency of the charges, which are different charges which are present, their actual charge values, the Boltzmann coefficient k, the temperature, the absolute temperature T, the dielectric constant d, and then finally things associated with this equivalent ionic radius which is in question. And finally we arrived at a very short, concise form of how to define the ion activity coefficient, which we used later on in several solved examples in order to evaluate the efficacy of each ion in the presence of each other. Okay. So we did some problem examples towards that direction, where we tried to see what is the effective influence of this activity coefficient onto the EMF generated at a particular electrode while sensing a solution. And in fact we tailored some problems wherein we mixed some 2-3 different ions of interest and tried to modulate before mixing and after mixing what is the contribution from the particular target ion because of a change in activity owing to the presence of the other ion. Okay. So we did a very important design step here, and this contributory equation was also called the Nikolsky-Eisenman equation, where we tried to find out what would be the contributing factor of one ion in the presence of the other. And in this light we also discussed something called the ion selectivity coefficient, and in fact the ion selectivity coefficient could be determined through a series of experiments, as was also designed earlier for different ionic systems. For example, if there is a sodium ion present and we want to measure the sodium ion's concentration, and we put a series of different ions like calcium ions, probably some chloride ions, some sulfate ions, some potassium ions, so on and so forth, and then try that at each level of mixing we try to find out what are the contributing EMFs which would result in some way for us to gauge what is the selectivity of the calcium ion over the other ions which are present in the system itself. So this in a nutshell completes our lectures 7 to 9 and also lecture 10. So, following this we will be doing another review session for the lectures to come later. Thank you.